Now, at first I was a little confused because I was like, well, in theory, what you should be able to do, and actually I got this work on a separate occasion, and I couldn't reproduce it for this because I didn't have enough time. But basically, I played a note, recorded the sound, and I was able to find the largest component frequency and say, that's the basic frequency of this note. And then what you can do is you can look on like the piano scale and see which note most closely matches that frequency. And you can say, you just played, you know, B sharp or whatever. And what I'm wanting to do actually eventually is, you know, do some kind of thing where I can like hum music into like an iPhone app or something, and it'll tell me what notes they are, something like that, some kind of cool thing like that. Now, in this case, it's a little bit iffy which one is. I mean, it looks like this one's probably the tallest at 100 hertz. But actually, I looked at the Moonlight Sonata music, and actually, this is a chord. It's two notes being played at the same time, so that's why it's a little. You see a lot more than one main pinnacle because it's actually two notes being played at the same time. But another really cool thing you can see when you look at this graph is you see all these spikes they're all evenly spaced out, and those are called harmonics. So you have almost any time you have a sound, you're going to have some other smaller frequencies which are also vibrating at the same time. It's hard to get anything in nature to vibrate without producing harmonic sounds at the same time. Now, one thing that's cool is, you know, if you have electronic music and you're producing stuff with math, let's say you just produce a simple sine wave at 100 hertz. What I found is it sounds really like this really annoying artificial sound. But when if you add harmonics into it, which is what natural sounds have, it sounds more full, which is really kind of interesting because almost everything has harmonic frequencies. And harmonics, by the way, are they're really interesting because that's where you get basically all music relationships. And harmonics are just, I'll just draw a little bit of the harmonic series. You have something that vibrates in this period, let's say this is a period. You have one vibration. Then you'd have another wave that vibrates twice. Yeah, I know. Oh, well, that would be like 4. So anyway, if you had 3, if that vibrated 3 times instead of 4, you know, that's kind of the relationships, and that's what harmonics are. They're basically ratios between the different frequencies. So I thought that was really interesting as well. So that's basically my presentation. That's I wanted to have a nice cool demo where I sing into the computer and it says A sharp or something like that, which I didn't have time to get working. But that's kind of where I'm wanting to go. So yeah, that's my presentation. Anyone have any questions?
Could you open up FFT4?
Yeah.
Is it possible to add labels to the axes on the plots?
It is. I can't remember how to do it though.
Could you? Would it be possible to take that wave you have there and then show what's the first approximation in the transform when it only has one coefficient, and then show it when it has 2?
Oh yes,
show when it has 3.
You can do that. Now with the fast Fourier transform, you can't because you don't have access to the algorithm. But yeah, you can definitely do that though. And then I know what you're talking about. Basically, if you do this where you have one coefficient at a time, then 2, then 3, you start to see these sine waves converging on the actual wave it's trying to represent, which is pretty cool.
It's the equivalent of a band pass or a filter, a frequency-based filter.
Mm-hmm.
So your fast Fourier or your Fourier analysis, you've got frequency, and at some frequency you cut it off. So you cut off some of the harmonics.
Right.
You lose some. That's what MP3s do. You
Right.
lose some integrity, some of that richness, supposedly, but supposedly it's sampled high enough, you don't
can't see here.
Right, like if you have if you have some frequency you're trying to represent and you want to only use 100 Fourier coefficients effectively, yeah, you're going to be able to represent most stuff, but not some of the really, really small things you might be able to otherwise represent.
There's that app where you can play music into it and it tells you what song it is.
Oh yeah.
How does that work?
I don't know. That might be something similar. Oh, another cool thing with Fourier transforms is if you have something and let me go back to the audio one. If you have, let's say you're trying to filter out some noise, like a white noise. Maybe you'd say, well, the white noise is at these really, really high. Let's say you think this right here, this is just noise. We can just remove it and then do the inverse Fourier transform, get back to the time domain, and you basically just filtered out that noise.
You have digital signal processors that do their real time thing.
Mm-hmm. Yeah. So.
I think another common use is vibration analysis on machine design. Trying to figure out, there's some type of vibration that's either causing disturbance or upsetting the process in the system.
That's how you represent fingerprints for machines too. So there's a lot of times when they'll actually determine the noise and they can fingerprint machines this way. And I think what they do is actually take the sound generated, create coefficients, and the coefficients become the stored fingerprint.
Oh, interesting.
So you can ID something by the sound.
And I suspect Louis tried to avoid harmonics when he built his bridges.
Yeah. Right.
Some good examples, though, that make really good movies.
Yeah, make great
harmonic bridges. Classic.
I actually do have a tuner app on my phone that I assume does the same thing, where you can play, where you can tune an instrument, play a key, and it'll tell you what key it is.
Oh yeah.
So now you have to do some overlay to brain waves and figure out how some people, like my wife, I can play any note on the piano, she'll turn her back and tell you what note it is. And
Oh wow.
Some people have
That's awesome.
pitch, that gift of perfect pitch. So there's two things, there's perfect pitch and there's one pitch.
Yeah.
Right.
Yeah. It's the training that's...
So Caleb, where else is this used in surprising ways that we could all appreciate it? How it makes our lives better?
Somebody have plants in the audience?
Let me see.
Well,
Okay, here's. I'll give you.
Somebody's running to the audience.
Used to improve the efficiency of a long-range bike ride.
Well, here's one thing. It probably makes it music.
Sing along the way? Sure.
Well, here's one way. I don't know this. I haven't looked it up, but I would assume things like auto-tune would probably use these kind of things where you can break it into its frequencies, and let's say Britney Spears is a little bit off. And this is where it is. Well, you can just shift it over a little bit, do the inverse, and then you've auto-tune. I assume that's how it works. I don't know.
I thought you said make our life better.
Well, it's better than listening to her out of tune.
So auto-tune, they actually do that to recording artists then?
Yes.
Oh, yeah.
And I knew that there was that Black Eyed Peas or something.
Pitch, essentially.
There's a Black Eyed Peas, I think, is one of the most post-processed bands. I remember reading someplace that they do. And when they listen to them live, they don't sound the same because of all the post-processing that goes on in all the recorded music.
I can imagine.
I think it would be great to actually understand. So one of the things you left me thinking was like try to understand how compression works.
Compression.
I mean, using what you just have here, kind of take it to the next level, trying to figure out not just examples, but say actually see it how it works, especially through a bandwidth, through the line. It would be interesting to see if you're just doing that. Then what exactly is being transferred? Just the coefficients, and then the other system's supposed to decompose it afterwards.
Wait, you mean transmitting sound over? Yeah, I mean basically, it's all.
It's a frequency. It's your sampling rate. You got to pick your highest sampling rate. So digital phones, everything picks a high sampling rate, and there's ways to pick that. But if you want more, simple compression, you take lower frequencies, and you don't have the higher harmonics.
Right.
So it's less data. But then when you add MP3 and other things on top of it, then you're doing some heavy-duty math that gives you the same quality with less data.
When you get an EKG, is that what they use? The
frequency.
Also, before we quit, I was going to just say this book. This is what I read to kind of give me a lot of this knowledge, and man, it was just awesome book.
Looks illustrated too.
Well, it is. It's got a bunch of these like little like anime style like Japanese cartoons. It was actually done by this group called the Transnational College of Lex, which is this group of Japanese people who they like to learn like 12 languages all at once, and they're fascinated with language and finding patterns.
Spoken languages or
spoken languages?
Like programming languages? No, spoken.
Spoken. And they're fascinated by finding what they believe that there's these universal principles in all language, similar to universal things in music. And in the book they actually show how, for instance, Japanese vowels and the English vowels are all the same. And they show how basically, looking at the Fourier analysis, you can see how they're equally, in a certain way, the vowels are all equally spaced. So they're about as distinct of different sounds as you can get, which is really interesting. But this book though, it's cool because if you look it up on Amazon, and you look at the reviews, people are just raving. They're like, this is the greatest math book ever written, and I totally concur. Like, it's the best math book I've ever read because it basically starts at basic algebra, and it goes through like trigonometry, calculus, a little bit of linear algebra, but the whole subject matter is Fourier analysis. But along the way, it shows you all these other types of math very, very intuitively. I mean, it helped me understand some things.
There's a website that I've seen that did similar things where it was just starting out with rocks and then it was doing very complex math by doubling each row down and adding them up, and it was fascinating. Well, it says what's that, nines? So when you do a number as a pattern of nines, I can't remember. You add up a number and it's the leftover nines. Casting out nines. There's so many patterns in math that are fascinating. And then you're trying to understand, oh, that's how it works.
Yeah. Well, I plan to use this book with Aston or arguments,
in a couple years.
Because man, it's so well written, very, very interesting. So I really appreciated that, and it also tries to give you a good understanding of math and what the role of math is in the world, and understanding these universal truths and relationships, and that's kind of what it's all about. But then you can also practically apply it as well, which is really cool. Yeah.
Thank you.
Yeah.
We're almost there.
The ordering is